In this video, we will consider a certain problem that we will solve using the calculus of variations, that is the Euler-Lagrange method. And the problem is called the minimal surface of revolution. The idea is this: you have 2 points. One is located at x1, the other at x2, first at a height of y1, second height of y2. And you want to find a curve connecting those 2 points. Then take that curve and rotate it about the x-axis so that it forms a surface of revolution. That is, if we have some curve like this and then rotate the entire setup, then it would look something like this. So this is a surface of revolution, and what we want is the minimal surface of revolution. That is, we want to find the curve y of x such that this surface of revolution that is formed has the minimal area. Now, one possible guess would be to have just a straight line connecting the 2 points. However, when we look at the area, we know that the area of the surface of revolution will depend on the radius. And here, the straight line has a large radius much of the time. If we want to decrease the radius, which will help decrease the area, we might opt for a curve like this. This still begins and ends at the appropriate points, but now spends a lot of the time with a small radius. This certainly helps decrease the area, but unfortunately, it increases the length of the overall path, which in turn will increase the area. So we have these 2 contradictory influences, and it turns out the best curve ends up looking somewhat like the purple curve that we drew at the beginning. But what is the equation of this purple curve? Well, we are trying to extremize a certain integral quantity. So let's use the Euler-Lagrange method. We would do so in 3 different ways, solving this problem, the same problem in 3 different ways, showing various things that you might come across when solving similar problems. The area of the surface of revolution is given by where ds is a little bit of the arc length along this curve, expressing ds in terms of dx and dy.